Good afternoon, everyone. My name is Dhananjai. You may call me DJ, and I'm here with my colleague Avi. We work at Motional, and we've been using Ray since almost 2 years now. So we are here to impart the learnings that we've had of developing Ray-based infrastructure at Motional. Just a brief introduction of the company. We are developing and commercializing driverless technology at scale, starting with robotaxis, which will be available through on-demand mobility platforms such as Uber and Lyft. The majority of the company is owned by the Hyundai Motor Group, with a minority share by Aptiv. Motional is not a newcomer to the AV industry. Its roots date back to the industry's first startups such as Nutonomy and Automatica back in 2015-16. We've had some of the industry-first partnerships and pilot programs as well, with the first ever robotaxi pilot launched in Singapore back in 2016, with the first ever US robotaxi pilot launched on the Lyft app in Las Vegas. In 2022, we made a significant leap in our industry partnerships by having an industry-leading 10-year agreement with Uber to have our cars on their app potentially in the future. We develop our cars in the Singapore Smart Factory by the Hyundai Motor Group, and we are getting ready for a big expansion in Las Vegas and Pittsburgh very soon. Just to recap from our presentation last year at the Ray Summit 2024, at that time we were sharing how adopting Ray has made a difference in our stack. So initially, we used to have these daily drive logs. A drive log is a collection of data collected from a driverless car on a trip. Let's say I go out right now around the block and I collect some data. So that's called a drive log. I'll be using that term quite a lot in the presentation. So we have these daily drive logs like a stream of river. It goes through a data warehouse, and then it goes through some training platform processes. Afterwards, it goes to the ML engineers. By adopting Ray, we were able to shorten this distance between the daily drive logs and the ML engineers, and that led to an increase in throughput by around 10x or so, and in turn it increased the number of requests also that the ML engineers were having for the platform teams. So that was mainly our presentation last year. You can look it up on YouTube. The agenda for today focuses on ML data preparation using Ray, where we will be discussing two of our Ray pipelines and sharing our learnings from them. Then finally, Avi will be sharing about the actor-based node initializer and data provider pattern that has proven out to be beneficial for long-running large-scale workloads in our case. I'll start with the ML data preparation. So the core challenge here is, as an ML engineer, you have, let's say, 10,000 of these drive logs, which are the data sets that I mentioned earlier, and you want to process them quickly and efficiently and reliably. So you have a job which is running for multiple hours, potentially a day or more than that, and you don't want any failures. These drive logs contain on an aggregate petabytes of data. We are pretty multimodal because we have a driverless car and we have multiple sensors on them like LiDAR, radar, cameras. So there is no dearth of data in our pipelines. Then you have, let's say, tens of thousands of these drive logs being processed in a single Ray job. Another complexity that comes is the highly variable data sizes per drive log. So let's say if you go out right now on the car, you might just make a very short 10-minute trip versus a very long trip of 3 to 4 hours. So there is a lot of variability in the data set, which makes it more challenging to orchestrate these tasks on a Ray cluster. The design that we have come up with and something that has worked out for us is based on two main components. First is the more fundamental Ray core-based orchestration of the processing of these drive logs. So let's say I have 10,000, or let's just say 50,000 of these drive logs, which are these individual data sets, and you have a Ray cluster. I think most of you would be familiar with this pattern of using Ray wait to limit the number of pending tasks. If not, you could check it out. It's one of the initial patterns that Ray documentation had come up with. So we use this to limit the number of concurrently processing drive logs at a time. So let's say you have a Ray cluster of 50 nodes, but you have 50,000 drive logs. You obviously cannot process all of that together in most cases. So we use this to limit the number of drive logs being processed at a time, like a sliding window. Then to process each drive log, we mainly rely on the Ray data APIs, such as your reads and maps and writes of the world. So all in all, in a nutshell, Ray core is the foundation of our pipeline for the orchestration of each of these drive logs. I'll go through the code in the next slide. So I'm going to walk you through an example where you have this task called run. It's the top-level task in your graph, imagine that. Then it's loading the drive logs that need to be processed. Then you define that, OK, I'm going to process 100 of them at a time. So you iterate over all of them, one at a time. Then using ray.wait, you limit the number of them which are being processed concurrently. And you return only one of them at a time. And as soon as that happens, you add another one in the queue. The logic of processing a drive log is encapsulated in another task called process_drive log. It's at the bottom. So that's what I'm going to move to in the next one. But before that, for the drive logs, since I mentioned that they are variable sized, I can't just assume that they are all going to process happily, across my cluster. Some of them are going to be big. Some of them are going to be small. So the resource requirement is different. So in our case, we have an estimate of the memory that we put for each drive log. And our remote task parameter called memory, it provides that. So we provide a memory estimate just so that the scheduler is smart enough to allocate or orchestrate the task more smartly on the cluster. Then for the Ray data part, we process a single drive log in the task process_drive log, which I had mentioned in the previous slide here at the bottom. So we mainly rely on the Ray data API, where you have, let's say, some data for sensors, some positions, some maps, et cetera, et cetera. And we do very basic things here, like reading, processing, and then writing. So you can imagine there are some map reduce operations happening there, and some writes, and some joining. If you don't know, since Ray 2.46, Ray supports distributed joins as well. So that's something that we've been trying lately. After the data set is written, we mark the writing or processing of that drive log as successful. Some optimizations that we make on the way. Since I mentioned that the drive logs are going to be variable sized, some of them are 3 hours, let's say, long, or some of them are just 10 minutes, we have found it beneficial to process the bigger drive logs first, assuming that you cannot process all of them together. So let's say if your cluster capacity is only this much, but your data set is this much, we process the biggest ones first to have more overlap in the computation, and that gives us a time saving. And that's something that we realized about a few months ago. So yeah, that's one of the optimizations that we make in our pipeline. Second is the use of the spread scheduling. As I mentioned earlier, we already use a memory-based allocation for scheduling the process drive log task, but we also use the scheduling strategy called spread. I think some of you might be aware of that. It reduces the impact of node failures. So let's say you have 100 or 200 drive logs being processed, and one of the nodes go down. Because of the spread strategy, the impact of that is reduced. That's something that could be useful for your pipelines as well if you're processing multiple data sets. All in all, it avoids resource hotspots. Another option that we are trying right now is the placement groups, but we are finding that it requires a little more maintenance, so we are not relying on that yet. Now, finally, for this pipeline, I would want to emphasize on the fault tolerance. It's a long-running pipeline with a large scale of petabytes of data. I don't want it to fail. You don't want it to fail, right? So the graph looks like this. You have the driver. That's where the user sends the command. And the run task that I had described earlier is orchestrated there. As soon as it starts running, it orchestrates some process drive log tasks, which in turn have the Ray data API being called with your reads, maps, writes of the world. Now, I don't want my pipeline to fail at any given point of time. I want the least possible likelihood of that. How do I accomplish that? If something goes wrong in the reading, like your cloud error, network error, or something, I enable retries over there. So any of the reads or map or write, I don't want them to fail. So I enable retries over there in that step. Now, if let's say the process drive log task gets out of memory or something because that node was under high memory pressure, again, I enable retries over there. If we move to the top, let's say the run task, that node got compromised due to some reason. I enable retries over there as well. But the catch is, if a retry happens at the run task, then my process drive log tasks will be restarted. I don't want all of them to restart. So there is some state checkpointing or job checkpointing, you could say, that happens so that my drive logs, which are processed already, I put them in a persistent storage and go through them first to see which of them are processed already and skip them in case of a retry. Then finally, in the worst possible scenario, if let's say the run task also fails due to a fatal error, some of which are the local raylet died error or a node died error, some of you might have encountered them in your pipelines, I enable a retry over that as well. So that, in a way, adds multiple layers of fault tolerance. And this has allowed us to move from a terabyte-scale pipeline, like you can say tens or hundreds of terabytes, to all the way to tens of petabytes, causing overall like 100x scale. And for the models, it has allowed us to have a deeper understanding of our data because we had so much of it, but we were not able to use most of it in most of the times. So we are able to use that data more often now. And of course, it has improved our models drastically. So that's my part of the presentation. Now I'm going to let Avi describe another pipeline to see how it has benefited us by using Ray.
Yeah, thank you, DJ. So as mentioned, basically what we are trying to do here is to apply all the learnings that we have so far and apply it to a downstream pipeline. So at that moment, what we currently have was a pipeline on Spark and EMR, and that takes the output of the upstream pipeline mentioned before and generate the model features. A couple of biggest pain points that we have for this pipeline is that it takes a week of inter-team coordination to get new data releases out. One of the reasons is you need specialized knowledge to work effectively on it. So not everyone understands PySpark in our company especially, and that makes experimentation difficult. So we have a goal to empower ML engineers through higher ownership of the data pipeline and ultimately improving the total turnaround time. And we think that this is possible through Ray's Python as first-class language approach because they will see the same Python function that they work with every day. So the guiding principle for this project is my favorite quote: make it work, make it right, make it fast. The idea is just if you start a project, just get the POC out of the door as soon as possible. So with that, let's start with iteration 1. So at the start, Ray data really helps us because it's very simple and quick to implement. And it allows us to focus on the transformation function, which is what we care about. So as you can see in the diagram, basically what we are doing is we have metadata that specifies which sample to process, and then we read it through Ray data read parquet, and then we have the two blocks of the transform. The first one is the IO heavy one, we say. So it loads all the data from all data sources, and then do some joins, and then some light cleanup, and then passes the result to a compute heavy transform, which will eventually transform it to model features. And then the DS write parquet will simply write those features as parquet files. And because transforms are just Python functions that are well understood by MLEs, so we also built an orchestration layer on top of this using Hydra, if you're familiar with it. So MLEs can just define their own transform if they want, and then just have it pluggable, replace, or whatever they want with it. So the result of this iteration is we have a pipeline that works. It's easily scalable, but only up to a certain point. And we found out that as we scale the number of samples, we start to see some problems. We have some worker OMs because, again, as DJ mentioned, the sample sizes are variable. So we can't tune easily. It's either that you are underutilizing the platform or you have good utilization, but you run out into worker OMs. And what's worse is we found out that the pipeline randomly hangs, especially as you start to process bigger and bigger data sets. So in our case, the worst one was when we were processing like 51 million rows, and it hangs at 99%. So at this point, we realized that relying on retries is insufficient when you're doing large data set processing. So we started out iteration to address these problems. So to address the OM and hanging, we control the concurrency using the Ray weight back pressure pattern described by DJ. And then we also implement state checkpointing, similar to what we had in the upstream pipeline as insurance policy, so you can just continue where you left off if the job crashed. So as a result, we still have a very similar system. The main difference is everything is now orchestrated by ray weight back pressure batch processing, and at the end we have a state checkpointing. So the result of this one is basically the hanging and worker OM issues are resolved, and we're now able to resume failed jobs thanks to state checkpointing. But we started to notice another challenge, which is the memory leaks noticed that we noticed on the Ray dashboard. And this triggers a race of data set size versus cluster size, because as you scale the number of data sets, if you use the same cluster size, the processing time gets longer. And then basically, as the cluster runs out of memory, the process will crash. At this point, since we have state checkpointing, it's still okay because we can just resume the last 5% or so. But since we plan to deliver this to MLEs, this is definitely not ideal because they will come to us asking for support. So one of the solutions that we came across was Ray remote max calls. But it seems to, well, not to have effect, but only when we set it to a very low number, then it works for us. But at that point, the performance got hit very, very badly. So we start iteration tree. And basically, we took a good look at our pipeline, and we noticed that load is actually constant for each run. We know how much data that we are going to process. And we don't actually need the elasticity of the cluster. We don't need autoscaling. So we had an idea. Why not just simply map the samples to create static actor pool and simply map the samples to it? By static, it is static. The number is static throughout the duration of the job. So what we did was simply to load the metadata as data frame, and then we map all the rows of those data frame into these actor pool. So the IO heavy one, compute heavy one, and we also changed the Ray data write parquet into a writer actor pool, and then have state checkpointing. So the result is happy faces. This is exactly how we felt at that point, and we managed to maximize the usage of our cluster, as you can see over there. Memory leak issue is fixed, and we have the performance increased by a factor of 2 compared to iteration 2. And at that point, our backend team was doing a cube ray upgrade, and this also brings us a free 1.3x speed up on top with cube ray. So that's a good bonus. So what's the final impact? When we compare this to the baseline pipeline, Spark and EMR, basically it's 10 times faster. Now processing years of Motional data takes less than half a day. And to our surprise, it's also more than 100 times cheaper compared to baseline processing. So just to give you a number, for a single run, it went down from 100K down to 1K. So that's really good saving. And most importantly, we achieved our goal, which is to reduce the total turnaround time from weeks to days, because now MLEs can just look at the pipeline and see, let's say I want to create new features, and then just do it themselves. So what's the takeaway? I think, at least for us, Ray data is a really good tool to get started with, but as you start to scale, the underlying complexity starts to show. As with anything, it's not a silver bullet, so you really need to understand your pipeline, where the bottlenecks are, and you also need to understand Ray data. So tuning, and for us, going off the beaten path may be necessary to achieve these results. But ultimately, we are happy with Ray. Ray adoption delivers significant impacts for us. Right, so now I'm going to share something, a pattern that we implemented that solved, this might be specific to us, but it's how we solve a certain data problem. So what's the situation? In our pipelines, we have a remotely sourced data that is used repeatedly. And the data requirement is unique to each job. So I know AnyScale has an initialization script that you can use, but this is not, we can't use that because the data requirement is unique. And to give you more context on this, because we are processing drive logs, each drive log will have different maps, for example, different sensor data. Yeah, so, and they can be large in size by nature. And the data is also shared between workers on a node. And the challenge for us was because the APIs providing this data were not in our control. And some of them are really not scalable, and we can't really access them in a highly concurrent way, in a horizontal way. So we even have this instance where we brought down the API apps infrastructure. We tried several things to fix it. First, we tried using a shared file system, EFS, FSX, but it lowers the performance. Or you can try using a network optimized instance, but then it will increase the cost. So what's the solution? So in some of our other pipelines, which runs on top of some bespoke solution that we have in the company, we usually preload the data into the disk of each node. So, but this is not easily, you can't do it easily on Ray, right? So what we did was we have one actor per node orchestrating the preloading of the data. And then all workers on those nodes will need to access the data through the actors. And we call it the node singleton, initializer, and data provider actor pattern. So how does it work? In the initialization phase, as mentioned, you get the job's data requirement. And then you detect the available nodes. For us, we do gang scheduling before the job starts. So all the nodes are there. And then we detect the available nodes. And then you launch one actor on each node. And then on those actors, you call initialize on those actors. And then at runtime, this diagram shows you how it works on each node. So simply, all the tasks, all the actors that process the data will request the data through the data provider actor. And since everything is cached locally, the data provider actor can just simply point to the path of the file and then can have the tasks or actors access it locally. And this gives you two benefits. The first one is it's fast because it's direct access. And the second thing is you save on object store memory, so you can use it for some other tasks. So I'm going to go through the implementation. So there are three parts. The first one is the data provider actor. So it's responsible for initializing a node by preloading a data and then providing a controlled way to access data to the workers. So as you can see here, there's this class, and we decorate it with Ray Remote. And I want to highlight that the maximum currency needs to be 1, but that's the default, just as a highlight. And then you have two functions, main function. The first one is the initialize data, which will download everything to disk. And the second one is get data, which will implicitly trigger the initialized data for auto-scaling purposes, and read the cache and return pointer. And the second implementation is the actor creation function, which is a global function with 3 key implementation points. The first one is get actor name, basically. So that ensures unique name in the cluster for each node. And then on the second part there, you'll see that it's the normal actor initialization function, but you add get if exists and name to it to ensure that it's a singleton across the cluster. And then you use the node affinity scheduling strategy and specifying the node ID and soft set to false, so it enforces the node placement. After the actor is created, you initialize the data, and then you simply return the reference. So the last part is the consumer. So, and this is an example class for it. Let's say it has a process sample function. The first thing that it needs to do is basically you get the node ID, and then you call the previous function which will get you the reference to the actor. And then you do a ray get on the get data, which will implicitly call initialize data if you need. Right, so takeaways. For us, node singleton initializer and data provider actor pattern is an effective way to initialize node with data requirements, especially ones with concurrency limitation, especially the ones that accesses API with concurrency limitation. Sorry about that. And using local disk cache allows fast access to the data without having to rely on object store. So yeah, we also have a feature suggestion for Ray. Yeah, maybe we need to do it ourselves, but yeah. Anyway, so it might be good to have init hook on node events, so users can just run code like this on node init, shutdown, etc. And we feel like having this feature built into Ray would be an even more robust alternative to the pattern. Thank you very much for listening. Yeah, now we are very happy to take questions.
Thanks for the great presentation. If anybody has questions, just raise your hand up. I've got 2 mics, and I'll come bring you one.
Thank you for the great presentation. So I'm curious, how do you store data in the drive log, the raw data from the vehicle, so that it makes all the downstream processing easier? What I mean is, ML engineers have diverse needs, like SQL-based metadata queries, time series queries, maybe some embedding search or text-based searches, and also all the future use cases that we don't foresee. So if you were to design the drive log for file format from scratch, or what you have right now, like how would you do that to make it flexible?
You want to take it?
So is the question about the drive logs being able to support multiple use cases?
Correct.
Right now, we just rely on open source formats, just like you have your Parquet format or having some indexing on top of that. That allows us to do more or less whatever tasks we are doing, like analytical or machine learning tasks, training, inference. I think you had a question about how would you redesign or something?
So on the vehicle, you store Parquet directly, or?
There is definitely some pre-processing we do from the vehicle. We collect the data, and then some pre-processing definitely happens.
Right. So I guess my question is on the when you collect the data on the vehicle, that format, how would you make your life easier when you do the pre-processing into Parquet?
Understood. I'm slightly far away from the visibility on what goes in those teams, but I agree with your point that if we had some direct format that can allow us to do things, directly, that'll be nice. But when the vehicle collects the data, it's not just the ML teams which use that data. We have many teams across the stack which use that, and the Parquet format might not be useful for them. So that whatever format is there, it's kind of fed to different teams so that it can serve multiple use cases. I think your question is still valid, that whatever that universal format that can satisfy everyone, we're still working on that, I would say.
Okay,
yeah.
Thank you. I have another question. You said you empowered MLEs to write these data pipelines. So the expectation on them is they write good code and optimized code. Because there are cases, like while I was working at a big company, MLEs write data pipeline code, but not to be optimized. Everyone has their own version, and infra team needs resources to support them and help them debug. So how do you balance between ownership, what parts they own, what parts the infra team owns, and how do you empower them to kind of write code that doesn't need maintenance?
Go ahead.
Right, so there are multiple parts to the answer. First, of course, we have a dedicated infra team sitting there, managing the array and all the resources, requirements, and everything. But on the MLE side, basically it's a simple code ownership. So you have the framework level ownership, and then you have the logic level ownership. So when usually MLE works on the second layer, they work on the the logic, how they want to transform the data, etc. And they can't, basically they don't have ownership to the pipeline part. So we kind of reduce their impact to just the logics. But yes, I see your point, because it can be less performant as before. But yeah, I mean, it's just a simple code review. So we will require them to prove that their new method or whatever is still as fast as before, or if they have a good reason to move to this new paradigm or whatever, yeah.
I could add another point to that. So in our ML teams, we tend to have 1 or 2 gluing engineers or bridging engineers, I would call them. I myself am like, I know ML as well. I've trained models and stuff, but at the same time, I understand Ray, so I'm able to write optimized pipelines. So that kind of helps in having that bridge in between the infra team as well as the ML engineers. That has worked out for us. Yeah.
Great. I think that's what we have time for. Thank you again, DJ and Avi, and thank you to everybody for attending.
Thank you.